I'm going to explain to you the properties in this figure. So, line segment AB is a second segment of circle Z, while line segment AC is an external second segment of circle Z. Now, the first theorem states that if two chords intersect in a circle, then the product of the length of the segment on one chord is equal to the product of the lengths of the segments of the other chord. Now, this is 2, this is 3, this is 4, and this is 6. Now, to derive this, line segment AB times line segment BC is equals to line segment DB times line segment BE. Now substitute. 2 times 6 is equals to 3 times 4. That is 12 equals 12. And that's a check mark. Now, other example. Well, this is 8. That is 4. This is 4, and that is 2. Now substitute. 8 times 2 is equals to 4 times 4. And that is 16 equals 16, and that's a check mark.
So let's take this another example. Line segment CD is equals to 2. Line segment AD is equals to 3. Line segment DE is equals to 9. And line segment BD is unknown. So, line segment CD times DE equals line segment BD times line segment AD. So, substitute. 2 times 9 equals to x, which is unknown, times 3. 2 times 9 equals to 18. X times 3 is equals to 3x. So, divide both sides by 3. Cancel. Is equal to x. And x is equals to 6. So, the line segment BD is equals to 6.
Theorem 2. It states that if two secants intersects at an exterior point of a circle, the product of the lengths of the two secants is equal. The formula for getting the product of the length of each secant is external second segment, which are line segment AD and line segment AB, multiplied to the total length of the secant, which can be get by adding the external second segment, which are line segment AD and line segment AB, and the internal second segment, which are line segment DE and line segment BC. So let's try this. Two secants intersects at an exterior point of a circle. The points were named A, B, C, D, and E. Let's say that external second segment AD is 2 and internal second segment DE is 7. And for the other secant, external second segment is 3 and internal second segment is also 3. AD, that is 2, times AE, that is 9, equals 18. AB, that is 3, and AC, that is 6, is also 18. So these two are equal. Another example. Two secants intersects at an exterior point of a circle. The points were named A, B, C, D, and E. Let's say that for secant AE, the measure of external secant segment AD is 3 and internal secant segment DE is 1. And for secant AC, external secant segment AB is 2 and internal secant segment BC is 4. Find the product of the lengths of the two secants. Line segment AD times line segment AE equals line segment AB times line segment AC. AD is 3 times AE, that is 4, equals 12. AB, that is 2 times AC, that is 6, is also 12. So these two are correct. Lastly, let's try solving for x. Let's say that external secant segment AD is 3 and secant AE is 8. And for the other secant, external secant segment AB is 2 and secant AC is x. Find x and check if these two secants is equal. So, line segment AD times line segment AE equals line segment AB times line segment AC. Let's substitute. AD is 3 times AE, that is 8, equals AB, that is 2, times AC, that is x. 2x, 24. Divide both sides with 2. So x is 12. Let's check if it's correct. AD, that is 3, times AE, that is 8, equals AB, that is 2, times AC, that is 12, equals 24. 24. So they are equal.
So the third theorem states that if a tangent and a secant are drawn to form an exterior point of the circle, the square of the length of the tangent segment is equal to the product of the lengths of the secant segment and its external secant segment. The formula will be segment AB squared is equal to segment BC times BD. AB is the tangent. BC is the external secant segment. And BD is the secant segment. Let's try with this example. Let's redraw the circle, tangents and secants, and name the points. Line A will be 4 centimeters. External secant segment is 2 centimeters. And whole secant segment is 6 centimeters. So let's follow the formula. 4 squared is equals to 2 times 8. 16 cm is equals to 16 cm. Next example. So let's redraw again. The whole secant segment is 5 centimeters, while the external secant segment is 4 centimeters. The tangent will be 6 centimeters. 6 squared is equals to 4 times 9. That will be 36 cm is equals to 36 cm. And that's correct. In this last example, the second measurement is unknown. So there are parts that are missing. Okay, so let's redraw the circle. Okay, wait a minute. So let's draw first the lines. This will be point A. This will be point C. B, and lastly D. Segment BC is equals to 4 centimeters. AB is 10 centimeters. And DC is unknown. The whole secant measurement is also unknown. So let's follow the formula. 10 squared is equals to 4x. So 100 is equals to 4x. We divided it by 4 to cancel out. 100 divided by 4 is equals 25. So the measurement of BD is 25 centimeters. AB is equals to 10 centimeters. BC is equals to 4. DC is still unknown. So what we are going to do is subtract BD from BC. So 25 minus 4. So DC is equals to 21 centimeters.
Theorem number 4. It is also called the two-tangent theorem. It states that if two tangent segments are drawn to one circle from the same external point, then they are congruent. Just like on the illustration, two tangents are drawn and their external point are the same, which concludes that they are congruent.
In theorem number 1, if two chords intersect in a circle, then the product of the length of the segments on one chord is equal to the product of the lengths of the segments on the other. If two secants are drawn to a circle from an exterior point, the product of the length of one secant and its external secant segment is equal to the product of the lengths of the other secant and its external secant segment.
If a tangent segment and a secant segment intersects outside the circle, then the square of the measure of the tangent segment equals the product of the measure of the secant segment at the external point. Theorem number 4 is called the two-tangent theorem. States that if two tangent segments are drawn to one circle from the same external point, then they are congruent.